It's often possible to draw the same Lewis structure with different arrangements of the electrons. So the atoms are in the same place, right? So we have the same arrangement of atoms, but it has different arrangement of electrons. And so when we have this situation, we call these resonance structures. Each resonance structure is known as a resonance contributor. Forgot to put that word on here. And actually the true structure of the compound is a hybrid or a fusion of all the resonance contributors. And then what we get is a structure that has sort of average bond strengths. So we're going to call this bond order. And we'll show you how to calculate the average bond order for a compound. So we're going to do nitrite ion. So we have to draw a skeleton. And in the oxoanions, oxygen is never the central atom. So we're going to draw nitrogen, and we'll draw oxygen on it, like that. We'll count up the total number of valence electrons. And so the total number of valence electrons, nitrogen, the central atom, has 5, so there's 1 times 5 for nitrogen. And then we have 2 times 6 for oxygen. Now, that doesn't take into account the negative charge. And in the rules, if you go back and look at the rules, you have to add or subtract electrons for the charge. So what we'll do then is go ahead and calculate this number, and you'll end up getting 17. And then what we're going to do is we're going to add 1 to give me 18 electrons. Okay, so this addition is for the charge. Now I'm doing this separately in this example, but at some point you're just going to do all of this together. You'll be confident enough, I think, when you do it, you'll just do it all together. Let me move the skeleton too a little bit, like this. So the next step is what we need to do is we need to figure out how many electrons you've already used up. So your skeletal electrons, there's 2 bonds and 2 electrons per bond, so that gives you 4. Okay, so this is number of bonds in the skeleton, and this is the number of electrons per bond. So if you look at the math and how that works out, the bonds will cancel and you're just left with the number of electrons. So you have 4 electrons used. And then you're just going to calculate how many you have left to distribute. And then that'll leave you with a total of 14. So what you do next is you distribute the remaining electrons. Typically we do the outside atoms first, and generally as I mentioned before, we'll be using electronegativity to determine like where the electrons go if there's a choice of different electronegativities. Here we have oxygens on both sides, so it doesn't really matter. So I'm going to go 1, 2, 3, 4, 5, 6. That completes my octet for that oxygen because of the 2 electrons in that bond. And then 7, 8, 9, 10, 11, 12. Now, when you run out of space on the outside atoms, then you move to the inside and you fill in electrons. So far I've used 12, so I have to add 2 more. And just as a check, the total should be 18, so you can count up pairs. There should be 9 pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, to verify that you have all your electrons in place. Oftentimes that's where people kind of mess up. They don't check, like, did the total come out correctly? Now when you check octets on this structure, what you'll find is the oxygens are happy, but the nitrogen is not. It only has 6, 2, 4, 6. So similar to how we dealt with nitrogen in N2, right? We're going to go ahead and take electrons from an oxygen and place them as a bond in between the oxygen and the nitrogen. That'll allow the nitrogen to have an octet. It doesn't change the count total for the oxygen. So when I do that, I'll get one structure that looks like this. So quite literally what I'm doing is just erasing it and drawing it like that. Okay. I want to leave the skeleton with all the electron works sort of clean so you have something to look at. And then you're going to put the nitrogen in the middle, pair of electrons on the nitrogen, and then we'll have an oxygen like this. Okay, so that's one structure. The other structure you could draw is you could have drawn it from this oxygen and put it in between rather than from this oxygen. So like this. It doesn't matter which pair you take. I've just by habit have always taken the bottom pair. You could take the outside pair or the top pair. This is not trying to imply the actual shape of the molecule. It's just an accounting of the electrons. One more thing we have to do. So if you think back, looking at the instructions, right, we checked for octets. Then we had to form a double bond because the nitrogen didn't have an octet. And then we are checking for resonance structures right now, and then we'll do formal charge. But since I could draw nitrite ion two different ways, right, it's the same structures, right, but a different arrangement of the electrons. So these are resonance structures. And the minimum number of resonance structures you can have is 2, because if it doesn't have a resonance structure, it's a single structure without resonance. We can't have resonance with except 2 structures at the minimum, I guess. Anyways, kind of weird to say that. So there's 2 resonance. Okay, and then I'm going to do a little bit more with that, but we got to do the formal charge. And then let's go ahead and do the formal charge for each atom. And then we're going to, on the next slide, talk about rules like how you know when the formal charge will be 0. So formal charge calculation will be right here. It's 6 valence electrons minus 2 for the bonds minus 4, so that's equal to 0. The nitrogen, 5 valence electrons minus 3, that's 6 electrons, 1, 2, 3, 4, 5, 6, but it's divided by 2, so it's 3, minus 2 for the lone pairs, and that's also 0. And then this formal charge, it's 6 minus 1 minus 6, and that's minus 1. Okay, so this oxygen with a single bond has a minus 1 charge on it, like that. So they're both the same. These are done and both have the same formal charge calculation. Now, if you look at the formal charges on the structure, right, you'll notice that it comes out to minus 1. And as a general rule, if you add the formal charges up, it equals the overall charge. So another way to say it is the overall charge equals the sum of formal charges. Okay, so there we have resonance structures. We filled in the formal charge. One last thing, and I mentioned this with ionic compounds. It's an ion, so you have to put brackets around it, like that. I didn't leave room for them in the middle, but when we draw resonance structures, we draw an arrow that looks like that in between to indicate that they're resonance structures of each other. The last thing to do is to calculate the bond order. Now, if this didn't have resonance, a single bond is a bond order of 1, and a double bond is a bond order of 2. Okay, and I'm introducing this terminology. It's actually something we'll use in the next chapter quite a bit. when bond orders are calculated different ways. But for now, a single bond is a bond order of 1, double is bond order of 2, and triple is a bond order of 3. Okay. Well, what is the bond order? There's a couple of ways you do this. One is to just look at the structure, right? It's a bond order of 2 in one structure. It's a bond order of 1 in another structure. And there's a total of 2 structures. So this is the sum of, it ends up being 1.5, sorry. But this calculation is the sum of bond orders divided by the number of resonance structures. And so you get a bond order of 1.5. Now, why is that important? It turns out when we look at the bond lengths, and we talked about atomic radii and stuff like that, turns out when you look at the bond lengths for these different structures, it turns out they're the same. And they're actually halfway between a single bond and a double bond in terms of their strength, or roughly halfway. And so what that tells us, it's like a bond and a half, right? And these two resonance structures represent sort of the extremes of the actual molecule. The actual molecule, when we fuse it together and get the average, is known as the hybrid. So the hybrid for this structure has a 1.5 bond here and a 1.5 bond here. And we'll spend a little bit more time in future chapters as well as this chapter talking about that. So here's an example for you to practice on. This is ozone from the upper atmosphere, and what I want you to do is draw its Lewis structure, find the resonance structures and formal charges, and then calculate the bond order for the oxygen-oxygen bonds. I should point out that the skeleton for ozone is like this. It's 3 oxygens in a row. Go ahead and do the calculations and draw the structures, and then I'll walk you through the solution. So here's the solution. Drew a skeleton, I already gave you that, and the valence electrons, there's 3 oxygens involved, so there's 18. I distribute them remaining electrons, which is 14 around the atom. But again, there's 4 in the skeleton when I started, so I distribute the remaining, and then I check for octets. And then what you see is very much like the nitrite ion. The oxygen, like the nitrogen in nitrite, is lacking an octet. And so it ends up sharing a pair of electrons on both the left side here with the oxygen on the left, and on the right side here with the oxygen on the right. And these are the 2 resonance structures. Now, this is not an ion, so that's why I didn't draw the brackets. Right here, I had to put brackets around it. Here, I don't. Then I have to check the formal charges, and the oxygen with the single bond, right, is -1 because it has 6 valence electrons, 1 bond, and 6 lone pair electrons. The one in the middle is 6 valence electrons minus 3 bonds minus 2 for the lone pair, or 1 or +1 in the structure. And the last oxygen you can deduce is 0 because ozone doesn't have a charge. This one's positive, this one's negative, so this one can't have a charge either. Otherwise, the overall formal charge, and some of the formal charges would not equal the overall charge. Now, for this structure, I'm just going to do it based on the structure at the bottom. This will be minus and plus like that. Now, the hybrid for this, I just want to draw it out for you, has bond orders of 1.5. Again, because this bond in one structure has a bond, so this is going to be the bond order. Oops, bond order. It has 1 in that structure. It has 2 in the top structure here. There's a total of 2 resonance structures, so it ends up being 1.5. Now the hybrid for this molecule is actually drawn like this. I'm drawing it bent in its shape because that's actually what its shape is. and then the electrons are distributed that way. Typically in the hybrid, you don't see the electrons drawn at the end because half the time the electrons are in a bond, right, and the other half of the time they're not. So this is typical of the hybrid sort of look. All right, let's talk a little bit about formal charge. Just by looking at structures, how do you know when it's not zero, or how do you know when it is zero?